Hi, thanks for joining me. Today I'm going to be showing you a cool theorem all to do with infinite series, and I'm going to be proving that theorem as well. Now this theorem was actually sort of a problem set in the international mathematics competition for university students. So this is kind of like the Olympiad, but for university students, and this was back in 2018. But that being said, the theorem has a really neat and quite concise proof, and yeah, I'm going to prove it today, but let me state what the theorem is. I'll give you a chance to solve it and then I'll prove it myself. Okay, so we have an and bn being sequences of positive numbers, and obviously that means because they're positive, that means they're also real. Okay, and we want to prove that the following are equivalent. So TFAE just means the following are equivalent. So we've got two statements here, statement 1 and statement 2, and we want to show that they're the same thing, or they're equivalent. Okay, so statement 1 says that there exists a sequence of positive numbers Cn such that the sum from n equals 1 to infinity of an divided by Cn and the sum from n equals 1 to infinity of Cn over Bn are less than infinity. So in other words, these two series here converge. Okay, so that's statement 1. And statement 2 says that the sum from n equals 1 to infinity of the square root of an over Bn is less than infinity. So this series here converges. We want to prove that these two statements are equivalent. So if you want to have a go at proving this theorem, pause the video now and give it a go for yourself. And I'm going to jump straight into a solution. Okay, so let's start by proving that if 1 is true, then 2 is true. So we're going to suppose that we have a sequence of positive real numbers, Cn, such that the sum from n equals 1 to infinity of an over Cn and the sum from n equals 1 to infinity of Cn over Bn both converge, i.e. they're both finite, because remember everything in this is positive, an and bn, they're positive sequences, and Cn is also a positive sequence. Okay, we want to show that the sum from n equals 1 to infinity of the square root of an over bn converges as well. Well, what is the square root of an over bn? Well, we kind of want to use the information we have up here, so that we can actually write this as the square root of an over Cn times Cn over Bn. Okay, this is for any n, because obviously the Cn's will cancel and we'll just get this thing here. But now we've got something which is the geometric mean of two numbers, so we can use the arithmetic mean geometric mean formula, which just says that the geometric mean is less than or equal to the arithmetic mean. So this thing here is less than or equal to the arithmetic mean of these two numbers here. So the arithmetic mean is of course just half one number plus the other, so an over Cn plus Cn over Bn. So this guy here is less than or equal to this guy here. Now we can just take the summations of both sides. So this implies that the sum from n equals 1 to infinity of the square root of an over bn is less than or equal to a half times, and now we can expand it as two different sums because everything is nice and positive, so we don't have to worry about silly rearrangement things. But this is less than or equal to the sum from n equals 1 to infinity of an over Cn plus the sum from n equals 1 to infinity of Cn over Bn. Now by assumption, this guy is finite and this guy is finite, so we're summing two finite numbers then dividing by 2. So this thing here is going to be certainly finite as well. Okay, so that proves that 1 implies 2. Let me clean up the whiteboard and I'll prove that 2 implies 1. Okay, so now we're going to prove the other direction, so 2 implies 1. So we're going to assume that the sum from n equals 1 to infinity of the square root of an over bn is less than infinity, so it converges, and we want to find, or we want to show, that there exists some positive, so there exists a sequence of positive real numbers Cn, such that the sum from n equals 1 to infinity of an over Cn and the sum from n equals 1 to infinity of Cn over Bn both converge. Okay, and this way is actually quite straightforward, because if we can just explicitly give a Cn, which has these properties, we'll be done. And in fact, we can just choose Cn is equal to the square root of an bn. And firstly, notice that this is well defined, because remember we require that each of the Cn's are positive. Remember an and bn are both positive, so you multiply them together, you get positive, and you take the square root, that's also going to be a positive number. So this is all well defined. So Cn equals square root of an over bn. Well, what's this guy here? Well, let's just rub this off and put an over bn, and this guy here is just an bn. Okay, then just using some standard root properties, this thing here becomes the sum from n equals 1 to infinity of just the square root of an over bn Okay, and we know that that's finite. Well, let's just check this one here. Well, this also becomes the sum from n equals 1 to infinity of the square root of an over bn. So the exact same thing as this thing here, and this, of course, is also finite by our assumption at the top. So we found a Cn, and we're done. That sort of solves the problem. Of course, we could use any scalar multiple of Cn. We could put a lambda here, where lambda is any positive real number, and that would also do. This one here would evaluate also to, well, we'd have a 1 over square root of lambda out the front here, but we can bring that to the front, and that, of course, 1 over square root of lambda is going to be positive, and here we'd have a square root of lambda as a factor, but they'd also be finite as well. But we only need to find one, and in fact we didn't need to find one, we just need to show existence, but to show existence it's sufficient to find one explicitly. Anyway, I hope you have enjoyed this theorem, this proof. For an international mathematics competition for university students, it's kind of a somewhat easy problem, but the result is quite cool that you've got a nice theorem. It probably isn't the most efficient if you want to show that a series converges, or show that the square root of an over bn converges where a and bn are positive real numbers. But you never know. If you find a fun sequence which has the properties that the sum... Sorry, if you want to show that the sum from n equals 1 to infinity of square root of an over bn converges, if you have a particular example and you find a Cn which satisfies statement 1, and from that you can deduce statement 2, I'd love to see it. But yeah, that's just a quick video for today. I hope you have enjoyed it. Thanks for watching, and I'll catch you in the next one. Have a great day.